Okay, so now we're going to work through the free response questions. Um, and I'm just going to walk you through my process. And if you have any questions, seek me out, let me know, and I'll try to clear up any confusion you might have with these. So the first thing I'm going to do is read through the question. We have a crate being pulled across a horizontal floor by a rope, and we have a massive crate M, so that's given. It's like they say the mass is 2 kilograms. It's a given value, even though it is just a variable. Coefficient of friction is mu. Hey, there is friction. That's something to pay attention to. And the tension in the rope is Ft. So with all forces problems, your steps are pretty much the same. Number one is clearly define your axes. And it could be the axes of motion, it could be perpendicular axes, but it's usually the axis of motion that we're most paying attention to. And if it's moving horizontally, that's the direction that it's moving. That's the axis of motion, and perpendicular would be the other way. Number two, we're going to draw a free body diagram. And number three is we're going to do net force equations. And we're paying specific attention to if there's multiple objects interacting, like two objects attached by a rope or two objects being pushed into each other, we're going to treat it as the net force of the system. So I'm just going to put that here just so I have it there and I remember it. And I can copy and paste those three steps, into pretty much any forces problem. So now we've gone through that, let's actually look at A, B, and C. Well, A, that's our free body diagram. B, compute the normal force, and I'm automatically thinking, okay, normal force is a vertical force, so I'm going to be doing a net force equation for the vertical forces. And part C, acceleration, which is going to be horizontal. That's the way it's moving, and that's going to involve horizontal forces. So for part A, that's simple. We have normal force up, we have the weight of the crate down, we have friction backwards because they mentioned, hey, there is this coefficient of friction. And I could have just written the lowercase f, and I could have just written capital N, and I could have written capital W. Again, you can have these variables as pretty much anything, except for this one because they specifically said, hey, it's Ft. But in previous problems, I've written it just as a capital T for tension. Again, you can use any terms you want, but that's what we're looking for. So that's your free body diagram. That's part A. I'm also going to break this diagonal force down because our y-axis is like this and our x-axis is like this. Tension does not fall along one of those axes, which means I'm going to break it down into its x component parallel to the x-axis, ftx, and the vertical component, fty. And hopefully you're already to the point where you realize, oh, if the hypotenuse is the full tension in the rope, then the opposite side would be the hypotenuse tension times opposite goes with so sine theta, ft sine theta. And similarly, ftx would be the hypotenuse times cosine theta. So that cosine and sine tell you how much of this is pulling in the adjacent side and how much of it is used to actually lift the box. So we've broken down our forces into x and y, or along our axes of motion. Part B, calculate the normal force. You can think about this one of two ways. Number one, if you're lost, you can jump right to number 3 and do your net force equation for the vertical forces. Or B, you can realize, hey, it's all of the acceleration is horizontal, which means the vertical forces, the forces along the y-axis, are balanced. Or normal force plus Fty have to balance out the weight. So you could say, okay, normal plus Ft cosine theta, ooh, my goodness, sine theta, have to balance out or equal the force of gravity. But we're given these variables, m, ft, theta, and g. And anytime they say, hey, solve for these in terms of these variables, at the bottom of the space, I like to write m, ft, theta, and gravity, write the variables that I'm allowed so that when I do get a final answer, I know if my final answer meets my expectations. So we're solving for normal force. So I'm going to bring tension sine theta to the other side, or subtract it from both sides, and I'm going to find that the normal force equals Fg minus Ft sine theta. So the question is, does our answer fall within our requirements? Fg is not one of our listed variables, which means I'm going to have to find a replacement for Fg that is in these terms. Well, fortunately, we know Fg is equal to mg. That's one of your basic equations that you should be very familiar with at this point. So that would be equal to mg minus Ft sine theta. And right there, well, that fits within our variables. So that's fair. We're good. We're done. So part B should be done for that one. But I told you there was another way. If you want to do this with net force equations, normal forces along the y-axis. So we're going to do net force for the y is equal to ma, your FMA equation. Net force equals mass times acceleration. Net force is the sum of all forces. And because this is vertical, that would mean normal plus Fty minus Fg equals ma. But the vertical acceleration is 0, which means the right side collapses to 0. And right there you get Fn plus Fty equals Fg. And that's the thought process we used behind the scenes to realize, hey, normal and Fty have to balance the weight. That's why we were able to make this skip in the beginning of part B. So following that same process, let's look at C. Compute the acceleration. So acceleration equals question mark. In terms of mass, tension, theta, the coefficient of friction, and gravity. So right there, I'm going to write those variables down at the bottom. M, Ft, theta, mu, and g. Because I want to be a reminder, my final answer needs to be in those terms. Again, following your steps. Axes free body diagram, net force equation. Net force equals mass times acceleration. But because the acceleration is horizontal, we're going to make sure all of these are in terms of x. So net force x equals m times the horizontal acceleration. Net force is, in its simplest terms, the sum of all forces, but we're looking at horizontal, so that includes friction, and Ftx. So negative Ff because it's to the left, negative Ff because it's to the left, plus Ftx, or we can just make the jump Ft cosine theta, equals m times the horizontal acceleration. And we're trying to solve for acceleration, so I'm going to divide both sides by m, and Ft cosine theta minus Ff minus the friction force divided by mass equals the horizontal acceleration. Fair, fair. Ooh, we're not allowed to use friction. So that we aren't allowed to use. I'm glad I put this at the bottom because I would have thought that I was done. So I'm going to move that down, and now we need to replace force of friction. So now I'm looking at my equation to the cheat thinking, okay, how can I replace force of friction? Or I'm looking at my free body diagram thinking, how can I replace force of friction? Well, fortunately, from your equation sheet, the force of friction is equal to the equation mu times normal force. Mu is given, but normal force is not. So now I feel stuck again, but then I realize, oh yeah, we solved for it in part B. So we can replace normal with mg minus Ft sine theta. Mg minus Ft sine theta. So mu times normal force, which is mg minus Ft sine theta. And there we go. Now we have friction, which we can plug back into here. I'll circle that, plug that in for friction. And let's take that equation, Ft cosine theta minus that whole mess, mu times the quantity mg minus Ft sine theta. Don't forget the whole thing was divided by mass. And that's your acceleration, which looks much more involved than it is. So hopefully that helped for this one. And let's jump to number 2. If you need to go back, pause it, rewind that section, and rewatch number 1. But I'm going to jump to number 2. First thing I do whenever I see a problem is look at the diagram. I see 2 blocks attached with what appears to be a rope and pulled with force F. I don't know if that F is a tension force or just someone grabbing the block and pulling it, but there is that force F. They label them block 1 and block 2 with mass M1 and M2. So there are no numbers provided in this question. So then I'm going to read the question, or actually I might peek at the answer or the questions that we're going to have to do. Label the forces, label the forces. What is the acceleration in terms? What is the tension between the blocks? Ooh, and if the string connecting the blocks were not massless but had M, determine a couple of things. Okay, so I'm not even going to look at 1 and 2. And again, when I'm looking at the questions, the questions that I actually have to answer, I'm just looking at them for 2 seconds to see what am I supposed to do. I'm looking for keywords. Draw and label forces, draw and label forces. I'm not actually taking time to think through them. It's just like, okay, keep this in the back of my mind. Free body diagrams, acceleration, find the tension. Now I'm going back. In the diagram below, a massless string connects 2 blocks, M1 and M2, on a flat, frictionless tabletop. Any time I see the word frictionless, highlight it, circle it, underline it, whatever you need to do so you don't forget it. You could even write friction equals 0, the coefficient of friction equals 0, or force of friction equals 0 if you're afraid you'll forget. I don't think anyone will forget because I think people will be excited that it's frictionless. And a force F. So they didn't tell us anything more. They just said, hey, there's a force F pulling it to the right as shown. So A, draw and label all forces on block 1. Let's look at block 1. In fact, we can do that right on our diagram. Nope, there's not enough room. But I'll copy and paste it below. Oh. All right, draw and label the forces on block 1. Well, it's being supported by the ground, so we have normal up. We have the weight of the block down. No, there is no friction, so there should be no force to the left. And we have this rope pulling it forward, which is pulling it with a tension T. Part B is asking us the same thing, but for block 2. For a massless string, those tensions are going to be equal to each other, because this rope has to pull all of the mass that's behind it and give it acceleration, whatever acceleration it may be. And it doesn't matter if you're at this end of the rope or the right end of the rope. They're both only pulling mass M1. So those tensions should be the same if the rope is massless. Now, knowing that, we also have normal force up, force of gravity down. Ooh, but now we have 2 normals which are not necessarily the same, and 2 weights which are definitely probably not necessarily the same. So I'm just going to call this Fn2 and Fg2. And then we have force F, which is already labeled. I feel weird not putting something on there, so I'm going to redraw that arrow in black for F, or red for F. And if you want, you could even put, hey, Fg2 is equal to mass times gravity, being careful which mass you're talking about because we have 2 different masses. Same thing for the one on the left. This is going to be equal to M1G. And I'm already thinking in the back of my head, vertical forces are balanced, right? So for block 1, the normal has to be equal to this M1G, and for block 2, the normal has to be equal to M2G. Thoughts that are going on in my head while I'm frantically writing things. But I figured I would fill you in on my thought process as I go. I'm actually going to take this whole thing and shrink it just so we have a little more room. Oh, can't shrink it. That's a shame. Part C, what is the acceleration? Acceleration is unknown, and now I'm feeling lost. How the heck do we approach acceleration whenever you're lost with a forces problem? These are the steps you're doing. Axes of motion, free body diagram, net force equation. That's your key to all forces problems. Excuse me, I got lost in my thought. So I'm just going to put that up here for me. What have you done? Okay. This is our axis of motion, this blue line cutting through the heart of this, because that's the way it's accelerating. So that's the axis of motion. We have our free body diagram, and now we need to... Oh, net force equation. And because this is our axis of motion, any forces to the right, I'm going to call positive. Any forces to the left, I'm going to call negative. And just like we highlighted here before, net force equation, if there's two blocks tied to each other or pushing into each other, it's a system of objects moving together, which means I'm going to do net force for the system. Net force for the system is mass of the system times the acceleration of the system. And I don't need to put acceleration sub s, because if they're all accelerating together, the acceleration of the system is equal to acceleration of the first block is equal to acceleration of the second block is equal to the acceleration of the string. So you don't have to put s for that, and that's why. So now going back to this, net force for the system, well, let's just add all of the forces. That's what net force means, right? So we have tension to the right, this guy. So plus Ft because it's to the right. We have this guy, which is minus Ft. And we have force F. Plus F equals the mass of the system, which is all of the masses that are being accelerated added together, which is m1 plus m2 times acceleration A. And if we're solving for A, then, ooh, internal forces will cancel each other out, which means those FTs cancel. Thank goodness. That makes this way easier. So you should get F equals m1 plus m2 times A. And then solving for acceleration should give you F over m1 plus m2, which covers us for C. And let's shrink this because we're definitely going to need more room for E. So D, what is the tension in the string? So now they want us to solve for an internal force. Whoops. Those are your internal forces. And internal forces cancel out when you're doing a system. So the only way that we can solve for internal forces, and hopefully we've discussed this in class enough, is your net force equation for any individual objects. And whenever I'm choosing which individual object I want, I think about which object has less forces acting along the axis of motion. For the first block, that's just tension. For the second block, that's tension plus F. If you do your math correctly, you should get the same answer with both of them. But because the first block has less forces along that axis of motion, that's the one I'm choosing. And your math will prove to be a million times easier with that. If you want to go back and double check with block 2 after I do this, please feel free. I don't think it's necessarily a value. I think it's more algebra than you get content knowledge out of, but that's up to you. So I'm going to do net force for object 1 is mass 1 times A1. But again, acceleration of object 1 is the same as the acceleration of the system. So if we look at the forces along the axis of motion, along the acceleration, the only force we have is tension. So tension equals m1 times A. But that's not one of the variables we were allowed to use. It had to be in terms of F, m1, and m2. So we need to get rid of A in terms of F, M1, and M2. Fortunately, we already have it. We solved for it in part C. So thank you, Princeton Review, for showing us what we had to solve for before we needed it. So it's M1 times F over M1 plus M2. You gotta be careful. Don't forget your subscripts when you're doing things like this. And let's shrink this just a hair. So now we have D done, and we can work on E. So now we're going to look at E1 and E2. They want us to find if the string were not massless. That's the big change. So now we have mass of the string attached to this. And what that does is means now tension 1 and tension 2 are no longer the same. Because again, the rope has to pull everything behind it at any individual location. So on the right side, that end of the rope has to pull the mass of the string and mass 1, whereas the left side of the string only has to pull mass 1. So tension 2 should be more than tension 1 if they're accelerating together. That's why a massless rope is important. That's why adding mass to the rope is also important. So knowing that, if the string connecting the blocks were no longer massless, and I'm going to switch colors just so it's easier to follow, but had mass m of the string, and they said m, but I changed it to mass of the string just so we don't get jumbled. For part 1, they want us to find the acceleration of block 1 in terms of, what is that? In terms of f, m1, and m2. So let's get working on that. Delete that. And I kind of jumped the gun and went into 2 before doing 1. That was a mistake. I lost where I was in my head. But for part 1, they just want us to find the acceleration of block 1. Well, again, we have multiple objects accelerating together, and looking at what we have over here, that means, hey, treat it as a system. So I'm going to do my net force equation for the system is mass of the system times acceleration, solving for acceleration. Net force is the sum of all forces. So we have tension 1 to the right and tension 2 to the left. But those are internal forces because right here, this tension 1 is to the right on the block, but the rope is going to pull, yeah, that's the tension on the block, but the block's also going to pull a rope with Ft1 equal, so there's still going to be internal forces and they're still going to cancel. External forces has to come from somewhere external, which means if we draw a box around the entire thing, friction would be external because it's coming from somewhere outside. But really the only force we have here, because thank goodness it's frictionless, is F. And that's going to be equal to the mass of the system, which is m1 plus m2 plus m times acceleration. And solving for acceleration, well, we just divide by the total mass. So acceleration should be equal to m1 plus m2 plus m F over all of that, sorry. Excuse me. And that's our final answer, sorry. All right, so we can shrink this to make room for part 2. And part 2 says the difference in the strength of the force that the connecting force exerts on block 2. Fancy for, hey, how much is this pulling block 2? Well, that's tension 2, right? Because as much as the rope pulls block 2, the block pulls rope 2. So the difference between the rope on block 2 and the rope on block 1. Anytime you see the words the difference in, and this will show up in several problems, just think back to math class. Difference means A minus B. So the difference in block 2 and block 1 is going to be, they're asking us to solve for what is T2 minus T1. And I'm going to move this up to give myself a little more room. So now we need to solve for T2 minus T1, but that really doesn't help me until I think, oh my gosh, what if we solve for T2 and T1 separately and then just subtract them at the end? So my goal is, okay, what is T2 and what is T1? Solve for those. And with internal forces, there's only one option. You need to do net force for individual objects. And again, we're trying to find T1 and T2 so that at the end we can just subtract them. So we need to find T1, and for that I'm going to look at the net force for object 1. So net force 1 equals m1a, and the only forces acting on object 1 along the axis of motion is tension 1. So Ft1 equals m1a, and if we're trying to solve for tension 1, we can plug in the acceleration that we got in part 1. So tension 1 equals m1 times this jumbled mess that we got in the previous problem. So m1f over m1 plus m2 plus m. So tension 1, done. Now we have to solve for tension 2 using the same process. Internal force, which means we're going to be using the net force on an individual block. So tension 2, net force for object 2 equals m2a. Well, a is known. Net force is the sum of all forces. So we have F, and we have tension 2. So negative ft2 plus F equals m2 times this massive an acceleration, F over m2 plus m1 plus a, or plus mass of the string, which I think I just started calling m halfway through this problem, but that's fine. But to solve for tension 2, we're going to need to rearrange the equation a little bit. I'm essentially going to bring this term, tension 2, to the right side by adding it to both sides, and I'm going to bring this third term to the left by subtracting it from both sides. And when you do that, you can double check your algebra skills, but you should get F minus m2F over the total mass. So now we have tension 2, and our final answer is, hey, tension 2 minus tension 1. So I'm going to take both of those values and subtract them from each other, which would be F minus m2F over total mass, m2 plus m1 plus m, minus tension 1, m1F over m1 plus m2 plus m. And you could find a common denominator and subtract a couple of terms. It's not necessary. Technically, we answered the question. Find the difference in terms of F, m1, and m2. Those are all of the variables we have. So if you wanted to call this solved, you could. If you want to make it look a little bit cleaner, yeah, you could find a common denominator by multiplying both the numerator and denominator by m1 plus m2 plus m over m1 plus m2 plus m minus this whole block, which I'm just going to write as Vujja, so I don't have to write it twice. So then you're going to get fm1 plus fm2. And by the way, I'm distributing. That's all I'm doing in this step. Plus or minus m2f plus m1f. Did I make a mistake? F minus. Oh, yeah. That's not a bracket. I need to be really careful about that. I put that bracket there so I knew what Vujja represented. F minus that, minus. So, distribute plus, or minus m2f minus m1f over our new common denominator, the total mass, m1 plus m2 plus m. And you'll see a couple of things will cancel out. fm1 will cancel out, fm2 will cancel out, and you do end up with a really clean acceleration of fm over the total mass. So I'm sorry I got a little bit jumbled with my thought at the end of that, but hopefully with rewind capabilities and all of that, you can track my thought process through that problem. Come on. And that concludes number 2. So let's jump into number 3 once I get myself a little bit more space. All right, 3A, 1 and 2. Again, anytime I see a question, the first thing I do is look at a diagram, mass 1 over pulley to object 2 at angle theta. And then I'm going to briefly look. Values of theta for mass 1 to accelerate up the ramp and slide up the ramp at constant speed. So this has a positive acceleration. This would mean acceleration equals 0. And part B is if the coefficient of friction between the surfaces is mu, derive but do not solve an equation caused it to slide up the ramp at constant speed. Ooh, good, constant speed. I like that. So now I'm going to read the question. Assume the pulley is frictionless and massless. Oh, that's all it is basic information. So part A has two parts, A1 and A2. And I'm just going to very quickly say, hey, I spent hours working on part 1, getting it wrong over and over and over, and then went on to part 2 and realized if you did part 2 before part 1, it makes part 1 really conceptually simple. So the takeaway I want you guys to get is if you're ever stuck on a problem, please don't burn hours. Go on to the next part and plan on coming back to it. And if you're still stuck after coming back to it, at least you went on and did the other parts, because even if you can't get part A, you can get points for doing part B. You can get parts for doing A2 if you couldn't do A1. So don't ever skip any part of any problem ever. At least draw a diagram, write an equation, because you can get free points for that. All right, so that being said, I am going to skip A1 just because I know that I struggled with it, and doing A2 makes A1 so much simpler. And the reason it makes it simpler is because the block is sliding up the ramp at constant speed, which means that the acceleration of the system is going to be equal to 0. That's the other thought I had is, hey, we have two loops connected with a rope, which means I'm going to treat it as a system. And again, following those 3 steps, axis of motion, net force of the system, or free body diagram, and then net force equation. Because we have a bent rope, our axis of motion is going to be this, because this block is going to accelerate this way, and this block is going to accelerate this way. So our axis of motion is along this bent axis. And you have to choose what's positive and what's negative. Well, I'm going to say any force that's clockwise, I'm going to treat as positive. Any force that's counterclockwise, I'm going to treat as negative. I hope I said that correctly. So then we've chosen our axis of motion. This way is positive, this way is negative, and now I'm going to start labeling my forces. Pulley is frictionless and massless, but that doesn't mean the surface is frictionless and massless. But they say right here, the inclined plane surface is frictionless. Find the angle that will cause the box to slide up the ramp at constant speed. And the reason this works is, as this gets flatter, box 1 is not going to pull counterclockwise as much. As it gets steeper, it's going to start pulling more until you go vertical, and now the whole weight is pointed down. So what is the perfect angle that means M1, the vertical or the horizontal component of M1's gravity balances out the weight of box 2? If that didn't make sense, go back and rewatch it. So we need to find the acceleration equal to 0, which means we're going to jump to net force because we're trying to find acceleration. And because we have multiple objects connected, net force is mass times acceleration, or system. So now FG1, which is going to be equal to M1G, right? I think we can fill that in. Complete your triangle, because this is going to be our y-axis on an inclined plane, and this is going to be our x-axis. Or this is our axis of motion, and these forces are perpendicular to that. I'm going to switch colors so it pops a little more. So we have FG1x, which is equal to the hypotenuse, M1G, times, and because theta's in here, this is the adjacent side, M1G cosine theta. This is the opposite side, so F1, ooh, I switched my x and y, I'm so sorry. Did this just die? 1 second. So now, again, I just switched my x and y. This is F1GY, which hopefully you guys probably realized, hey, this is along our bent y-axis, so that's F1GY. This is FG1X, which should be M1G sine theta. Cool. So we've broken that down. We also have normal force because it's resting against the surface. We have tension up. And that covers it. For box 2, we have tension up, and we have the force of gravity 2 downward, which is going to be equal to m2g. Force of gravity is mass times gravity. And hopefully at this point you're remembering from the last problem, hey, those tensions need to be the same because it's a massless string. That makes this problem doable. So again, we're doing part 2 first. We're solving for theta. That's what we ultimately want to find. But I was lost. I wouldn't know what to do, but following your steps, axis, free body diagram, net force will get you to the answer in almost every situation. Net force of the system are all forces along our axis of motion. And that would consist of Fg1x, tension, tension, and Fg2. This one, Fg1x is to the left, tension is to the right, tension is to the left. Hey, internal forces cancel, plus Fg2 equals mass 2 times acceleration, but because it's constant speed, that means they're balanced. Acceleration is 0, equilibrium. So now we have Fg1 negative Fg1x plus Fg2 equals 0. But again, we don't have theta in there. Yes, but we know Fg1x is m1g sine theta. So negative m1g sine theta plus m2g, replace Fg2, equals 0. We can bring this to the other side. m2g equals m1g sine theta. And divide both sides by m1g. G's will cancel. And you would be left with m2 over m1 equals sine theta. And I'm just going to flip sides, so theta is on the left side of the equation. You don't have to do that. But they didn't want sine theta, they wanted theta. So we have to undo the sign. But whatever you do to one side, you have to do to the other. So you're going to get theta is sine negative 1 of m2 over m1. And that's the angle that will keep it in equilibrium. And let's read part 1. Accelerate up the ramp. If this is the perfect angle, let's say that angle, let's say mass 2 was 10 kilograms and mass 1 is 20 kilograms. If you did sine negative 1 of m2 over m1, you would get a number that exists. And you would find that the angle that keeps it perfectly aligned with these two masses, theta, would be 30 degrees. This is not part of this problem. This is me showing you what I mean. So if this is a 30-degree angle that keeps it perfectly balanced, if you make it flatter, what's going to happen? Well, weight 2 is not going to change, right? Fg2 doesn't change. But Fg1x gets smaller. So as this gets flatter, less of the weight is pointed down the slope. So if it gets smaller, it should accelerate up the ramp. Just like if you had a book that was perfectly balanced, if you made it steeper, it would slide this way. But because we have this upward Fg2, if you make it flatter, now Fg2 will be bigger than Fg1x. So any angle that's smaller than that should make it accelerate up the ramp. And that's all you have to do for E1 is, hey, theta could be anything less than this answer we got in E2. Sine negative 1 of m2 over m1. And that covers us for E2. So let's shrink this to, or at least move it over to make room for, or A2, sorry, A2, not E2. Let's make room for part B. And what do we need to do in part B? Coefficient of friction between the surface and the inclined plane is mu. So now we have friction here. We don't know if it's up the hill or down the hill, because if it's sliding down, friction would be working against it, friction would be up. If it's sliding up, friction would be going down, because friction is a resistive force. Derive, but do not solve. That just means, hey, find an equation satisfied by the value of theta that will cause it to slide up the ramp at a constant speed. Constant speed, acceleration equals 0. And again, axis free body diagram, net force. Well, they said up the ramp. That means friction is down the ramp. And part 3 of that process is net force equation. Well, we have multiple objects connected to each other. So net force of the system is mass of the system times acceleration, constant speed. Right side of the equation collapses to 0. Left side of the equation is the sum of all forces. So we have negative FF minus FG1X plus FT minus FT, cancel, plus FG2. And now plugging in our values, what are we solving for? An equation satisfied by the value theta that will cause it to slide up the ramp. So friction, from the last problem we saw, friction is equal to mu times the normal force equals mu Fn. So plugging in for this, negative mu times normal force, but we don't have normal force. But we know, hopefully, from the diagram, that normal force is going to have to perfectly balance the y component of the weight of box 1. So normal force is going to be equal to m1g cosine theta. So negative mu m1g cosine theta minus fg1x minus m1g sine theta, yikes, plus fg2 plus m2g equals 0. Terms 1, 2, 3. Terms 1, 2, 3. All I did was plug them in. Oh, that's going to be a mess to solve for theta, but derive, but do not solve. If you ever see but do not solve, I would circle it because that would save you hours. I would have spent a ton of time trying to solve for theta on this, and that would be a mistake. This is our answer. Done. All right, final problem, 4A and 4B, which this is the fastest problem on here. It used to have a kinetics version, but because we're now doing forces before kinematics, not kinetics, you only have A and B for this one. Skydiver is falling with speed V0. By the way, that is a 0. Anytime you see a subscript that's a number, that usually implies the time. So V0, that's the initial speed, the speed at time 0. So the speed when you start observing the situation. At that moment, at time t equals 0, she opens her parachute and experiences the force of air resistance that is given by this equation. K is a proportionality constant, so that's a constant, that's not going to change. And V is her speed. So as she goes faster, her velocity gets bigger. If velocity gets bigger, the right side of the equation gets bigger. That means the drag, the air resistance, gets bigger too. So the faster you fall, the more air resistance you experience, which makes sense. The faster you're going in a car, if you stick your hand out of the window going slow, it's like, that's a little bit of air resistance. But you stick your hand out of the window at 95 miles per hour, it's like, you feel it, right? Okay. So the total mass of the skydiver and her equipment is m, and g is constant. So A, draw and label all forces. I like free body diagrams. So we're going to draw her flying through the air with her backpack, and we have force of gravity down, and we have F up. They just called it F for air resistance. If you want to put F air, I think that's pretty fair. I think that's okay. Done. Determine the skydiver's acceleration in terms of m, v, k, and g. So part B, we're trying to find acceleration. Well, that's step 3 in our 3-step process. Net force equation. Net force is mass times acceleration. And net force is the sum of all forces. I'm going to choose up as positive and down as negative, just because math does it that way too. So we have the air resistance up, and we have the force of gravity down is equal to ma. But we're not allowed to use F air. We're not allowed to use Fg, so we need to replace both of those. Well, they already told us F air is equal to kV. And we're not allowed to use Fg, but we always know the weight is equal to mass times gravity. So kV minus mg equals ma. Solving for a, kV minus mg over m equals a. Done. I hope that video helps. I hope that gets you somewhere. And if you have questions, go back, rewatch it, or send me a message. I will be around. I'll try to make myself available. Let me know. And good luck. If you made it through all of this, ask me for some candy, and I'll give it to you. Bye.